Hey, let's now bring recursion to life by solving a couple of real problems. Problem 1. Factorial of a number. Let's warm up with something basic. Computing the factorial of a number. You've probably seen this before. 5 factorial means 5 times 4 times 3 times 2 times 1 equals 120. I ask you, how would you do it in code? Iterative approach, bottom-up thinking. Bottom-up means we start from the smallest pieces we already know and build our way up to the final answer. We'll use a loop to compute the factorial. Start with a result of 1 and multiply by each number from 1 up to n. Let's dry run it for n equals 5. Result equals 1. I equals 1. Result equals 1 times 1 equals 1. I equals 2. Result equals 1 times 2 equals 2. I equals 3. Result equals 2 times 3 equals 6. I equals 4. Result equals 6 times 4 equals 24. I equals 5. Result equals 24 times 5 equals 120. Final result, 120. Key points. Method, use a loop. Space used. Constant, big O of 1. Style, bottom up. We build our answer starting from the simplest case. Now, let's see the recursive approach, top-down thinking. Top-down means we start from the problem we're trying to solve and break it down into smaller subproblems. If I ask, what's factorial of 5? The computer says, I don't know that yet. But if you give me factorial of 4, I'll multiply it by 5. Let's dry run this step by step. Factorial of 5 equals 5 times factorial of 4 equals 5 times 4 times factorial of 3 equals 5 times 4 times 3 times factorial of 2 equals 5 times 4 times 3 times 2 times factorial of 1 equals 5 times 4 times 3 times 2 times 1 time factorial of 0. Factorial of 0 equals 1, base case. Now, results bubble up. Factorial of 1 equals 1 times 1 equals 1. Factorial of 2 equals 2 times 1 equals 2. Factorial of 3 equals 3 times 2 equals 6. Factorial of 4 equals 4 times 6 equals 24. Factorial of 5 equals 5 times 24 equals 120. Final result, 120. Key points. Method, break the problem into smaller recursive calls. Space used, big O of n. Each call adds to the call stack. Style, top-down, start from the big question and trust smaller pieces to solve themselves. Which one's better? For small problems, either works. Iterative is more memory efficient. Recursive is more elegant and expressive, but can be slower due to overhead. Now let's see the complex recurrence, that is real-world pattern. Let's try a real-world style recurrence relation. Problem. F of n equals 2 times f of n minus 1 plus 3 times f of n minus 2, with f of 0 equals 1, f of 1 equals 2. Find f of 5. Iterative approach, bottom-up, dry run. We'll build the result using only the last 2 computed values, just like Fibonacci. Start. f0 equals 1. f1 equals 2. Step by step. I equals 2. f2 equals 2 times f1 plus 3 times f0 equals 2 times 2 plus 3 times 1 equals 4 plus 3 equals 7. I equals 3. f3 equals 2 times f2 plus 3 times f1 equals 2 times 7 plus 3 times 2 equals 14 plus 6 equals 20. I equals 4. f4 equals 2 times f3 plus 3 times f2 equals 2 times 20 plus 3 times 7 equals 40 plus 21 equals 61. I equals 5. f5 equals 2 times f4 plus 3 times f3 equals 2 times 61 plus 3 times 20 equals 122 plus 60 equals 184. Final result. F of 5 equals 184. Why it works? We store only the last 2 results at a time. It's fast, memory efficient, and scalable. Recursive approach, top-down dry run. Let's call f of 5 and break it down recursively. F of 5 equals 2 times f of 4 plus 3 times f of 3. F of 4 equals 2 times f of 3 plus 3 times f of 2. F of 3 equals 2 times f of 2 plus 3 times f of 1. F of 2 equals 2 times f of 1 plus 3 times f of 0. Now use base values. F of 1 equals 2. F of 0 equals 1. F of 2 equals 2 times 2 plus 3 times 1 equals 4 plus 3 equals 7. F of 3 equals 2 times 7 plus 3 times 2 equals 14 plus 6 equals 20. F of 4 equals 2 times 20 plus 3 times 7 equals 40 plus 21 equals 61. F of 5 equals 2 times 61 plus 3 times 20 equals 122 plus 60 equals 184. Final result, F of 5 equals 184. But we ended up calling some values multiple times. This becomes inefficient for large N. Comparison recap. Iterative approach. Time complexity, big O of N. Space complexity, big O of 1. Pros. Fast and memory efficient. Suitable for large inputs. Cons. Slightly more manual setup. May feel mechanical. Recursive approach. Time complexity, big O of 2 to the power N without memoization. Space complexity, big O of N due to the call stack. Pros. Elegant and expressive. Matches natural mathematical definitions. Cons. Slower due to redundant calls. Risk of stack overflow if N is large. Final recap. Core difference. Iteration builds from the bottom. You take control and construct the answer step by step. Recursion breaks from the top. You ask the system to handle the details of each smaller piece. One is mechanical, the other is philosophical. Rule of thumb. Use recursion for tree-like problems, divide and conquer strategies, and elegant problem breakdowns. Use iteration for linear problems and optimize performance.